Hello, my name is Yoichiro Dobashi from Tokyo. For the first, I'd like to say thank you for giving me this opportunity. After graduation from master degree, now I work as a construction engineer in the design port and harbor. Japanese infrastructure is relatively complicated because of the demanded that structure must have high durability against tsunamis, earthquakes, and storm surges, sometimes at once. So there is no achievement of own contribution to this community now, but here I've prepared a comment from the previous work. The title is Using Numerical Ocean Bottom Pressure Models to Understand Time Series Recovered from the Diverse C4 Setting. I think the situation and size setting depends on seismic activity, volcanic activity, physical oceanic process, and gravity field change. But no matter what the setting is, using a numerical model to understand the variation is basic idea. So I introduced some recent research and comment. Firstly, this slide shows the target of OBP variations as a C4 geodesy, volcanic and seismic activity is the main target. Each phenomena has own amplitude and temporal variation. And the researchers have own target. I denote on this blue text show the typical target, amplitude, and same time scale. So in this presentation, I'll decompose the OBP variations with this target in mind, then introduce some recent topic and summarize. From this slide, I'll show you the component of OBP variations. OBP, ocean bottom pressure, is contain lots of phenomena. If we want to detect small vertical displacement, we should eliminate the other components from large to small. Pressure variation is denoted by this delta PV, and it consists of geophysical component, tidal component, cluster deformation, and tidal oceanic variation, and atmospheric pressure loading, and non-geophysical component like instrumental drift. In this talk, I'm gonna focus on the geophysical components, so I don't mind this one. Also, I don't care the tidal component because it is typically removed by using low-pass filtering or tidal model, so I don't care. But in this step, we hardly discuss the detail of split tides, but the more precise the analysis can be, the importance of the tide manner becomes. For instance, the deep sea sites for volcanic observation tend to be quiet from oscillation and be wired longer period observations. In that case, we should pay attention to long period constraint, which is not considered in some applications. We should have this sense commonly. Then when using numerical models to assess the cluster deformation, this delta PC, two components, this non-tidal variation and atmospheric loading are regarded as the main noise. Here is a detail of non-tidal component focusing on the non-tidal variation, this purple one. It is well known that the wind stress causes relatively short OBP variation well, and it is calculated well, relatively well by single layer ocean model and multi-layer ocean model either. But the other is a bit complicated, and I denoted as this number 2. This variation is related to water density change and ocean C4 interaction. This ocean C4 interaction. When considering density structure, it is easy for us to simplify the ocean into the 2-layer structures. This surface pressure and this subsurface pressure. This subsurface pressure reflects density distribution below the sea surface. Generally, the lower layer, this blue one, reacts in a direction that cancels out the upper layer. When the ocean is deep, the response is very accurate to cancel out each other. But as the seafloor is tilt and slope, there will be a shift in the response of the lower layer, which will show up as a pressure fluctuation on the seafloor. The bottom pressure gauge field it as a pressure and could mask crustal deformation. And the atmospheric pressure loading also has impact to OBP variation in short period, less than 10 days. When the inverted barometer response is established by water's complete reaction to air pressure like this, a high pressure coming, water level drops, and vice versa. The seafloor hardly feels the atmospheric pressure loading, but this IV response isn't perfect, so this term exists as an external force. My previous research, Dobashi and Inazu, 2021, assessed the non-tidal variation by OGCM, ocean general circulation models, and single-layer ocean model, how they can improve detectability. As a result, I realized that wind is the main component of ocean bottom pressure variations, and to subsurface related phenomena seem to be challenging to predict by multi-layer model now. And 3, atmospheric pressure loading shouldn't be neglected as an external force. Actually, in this research, OGCMs didn't improve the detectability well comparing to single ocean layer model, but OGCMs have potential to predict realistic bottom pressure, and they have potential to support to understand subsea seafloor processes. These 5 years, researchers frequently use a numerical model, ocean bottom pressure model, or related model. Target is this blue one is oceanic physical processes. This gray one is gravity change, and this red is a seismic activity, and yellow is a volcanic activity. I gathered the report and categorize them in this 3 regions: offshore, continental slope, and nearshore, reflecting the setting of observation sites whose characteristic of variation is a bit different. This board shows that volcanic activity and gravity change observation are being studied in OS. Seismic activities is in GS. Also, oceanic physical processes is being studied in OS, offshore, and also in continental slope for analysis of phenomena affected by topographic change, such as coastal trout wave. Actually, in the gravity change observation, there are lots of observation results all over the world. It is scattered, and it's containing a CS and NS site, but it is not easy to extract and evaluate that result coming from CS and NS, because the research purpose is not at the point, but two-dimensional in the case of gravity variation. So we should connect the information OS, GS, NS by classifying the result of recent observations and looking at them cross-sectionally. It is possible to understand seafloor pressure fluctuations continuously. It is also possible to obtain information on the performance of models for each classifications. A lot of information is available, but cross-sectional comparison hardly being made now. In this slide, I'll describe the differences in the characteristic of the C4 setting that we have just classified. Wind stress and atmospheric pressure loading are the main variabilities in OBP, and they are commonly important factor in all areas. In offshore, the water depth is deep, and the stratification of the ocean is so strong, so that even if the sea surface water level change due to the density change, the surface variation, this blue, compensate for it. Therefore, the amplitude is relatively small, making it a suitable condition for several pressure observation. And the observation of volcanic activity is usually carried out. On the other hand, in the near shore has shallower water depths, which means that sea level fluctuations are not compensated much and more observed as seafloor pressure. The original, the original amplitude is so large, and the spatial variation scale is small, I think, making it unsuitable for geodetic observations. But the on-land system could cover this region. In the continental slope region, there are uncompensated residuals of surface pressure and subsurface pressure appears as a seafloor pressure. The spatial scale is also small than that of weather-driven variability. It makes difficult to evaluate. On the other hand, the important factor, seismic cluster deformation, is just observed here. That is what makes the continental slope an important and challenging region. Finally, I introduce some concrete case. This is an illustration of how the sea level variation is much smaller at the seafloor in the offshore, compensated by the subsurface. The top figure is standard deviation of the daily output of sea surface height from the echo to echo. The bottom is the daily output in ocean bottom pressure, and the color bar are equal. It can be seen that ocean bottom pressure, the amplitude is considerably reduced from SSH. Since this is a global output, the situation in CS and NS is unclear, but it can be seen that in the OS, the large portion of the amplitude is compensated. This figure shows the comparison of Grace daily solution and the global ocean model variability for the top three is a multi-layer ocean models one, and the bottom one is a single layer ocean model. In previous study of global gravity field variability, atmospheric pressure loading has been considered as an external cause to reproduce more realistic seafloor pressure variability. In this study, the effect of pressure loading is taken into account in all models. So even in a shallow area we focus, we should consider it. This is a recent numerical model approach in the continental slope flying subduction zone. In this research, it is shown that seafloor pressure fluctuations, which are mainly driven by wind stress, can be removed with some accuracy by numerical ocean models. But the seismological requirement, residual RMS 1 centimeter, has not been achieved. Therefore, weather-driven seafloor pressure is removed from pair site as spatially common, and the seasonal variations that can't be removed by difference method between pairs are evaluated using the numerical ocean model. Although my previous research focused on just 3 days to 90-day time scale, in this study using a nearly identical model line up to more longer time scales. The longer the time scale, the more the multi-layer model represents phenomena that the single-layer model cannot represent, like the density fluctuations, meandering currents, and the eddy development processes. Therefore, it is a logical approach. It is a logical approach to look at the long period phenomenon in a numerical model. And this is my summary. In this presentation implies that what is occurred in each area in geodetic timescale, and implies that the difficulty of detecting deformation less than 1 centimeter in continental slope is challenging. And also, I know that cross-sectional view, like this workshop, is so important for American researcher and other countries' research. Important for sharing senses, what is difficult, how important, and creating scenario. And finally, a numerical OBP modeling for pressure geodesy in not many fields is useful for understanding the background environment of pressure gauges and improving the detectability of seafloor deformation from single observation site. It is still important, I think, and useful for related observations like borehole pressure observations or even incrementers. That is finished my presentations. And my boss, Daisuke Inazu, sent me a flash talk. So if you are interested, please check it out.